Okay, so good morning everyone. So we were looking at the natural proof barrier result due to Rasborov and Rudik, and what we showed that under the assumption of this lemma we can actually prove that uh, there does not exist any natural proof separating NP from P slash poly unless you can break one-way functions. Okay. And what this lemma says is basically that, well, if one can break a pseudo-random function generator, okay, so this is basically a pseudo-random function generator. So basically one can distinguish between a function that is truly random versus a function that is drawn from the distribution psi y, okay, then one can actually break a pseudo-random generator. Okay, so phi is a pseudo-random generator. One can show that its hardness is also bounded. Okay, so breaking a pseudo-random function generator gives one a way to break a pseudo-random generator as well. Okay, so that is the intuition. I can just write it over here. So implies one can break a pseudo-random generator. So this is roughly the intuition. So now let's look at the proof. So just let me recall what this distribution psi y was. So we have this function phi. Okay, we can think of breaking the output of phi into two parts. Okay, so we can think of breaking phi of y as phi 0, phi 1 of y. And now given any x belonging to 0, 1 to the power n, depending, and let's say that x is equal to x1 up to xn, what I can do is I can build this function psi xy, that is, we can think of it as being indexed on x now as psi n composed with psi xn. So look at the or we can look at it from this side. So let's say psi x1 of y, compose that with psi x2 and so on up to psi xn. So this gives us a k-bit string. Okay, and now we can just define psi y. So if y is chosen randomly, so with respect to y, I can define this to be a map from 0, 1 to the power n to 0, 1. So essentially what we do here is that not just we take this string, but we take the first bit of this string. Okay, so this basically gives us a map from x comma y to 0, 1. That is how we defined it. So now this gives us a distribution over functions. I can choose a distribution. I choose y randomly, and this gives us a way to choose a function from distribution. And now what we are saying is that if I can distinguish between these two functions, then I can break a PRG phi. Okay, so let's look at the proof of the lemma. So first what we will do is we will construct a tree. Okay, so let B of n be the set of all binary strings of length at most n. Okay. So what is the cardinality of B of n? So B of n will have 2 to the power n plus 1 minus 1 many strings, right. So now corresponding, so we'll build a complete binary tree of depth n, each of whose nodes will correspond to one binary string. Okay. So if I have a complete binary tree of depth n, it has this many nodes. Okay. So the number of leaf nodes is 2 to the power n. So each of my leaf nodes will correspond to a binary string of length n, and the internal nodes will correspond to binary string of length less than n. Okay. So it is built in a very, I mean, in the most natural manner. How do we define it? So we build a binary tree T corresponding to Bn. So the root of T corresponds to the empty string. Okay, let's call it I've used epsilon. Okay, I've not used epsilon. Okay, corresponds to the empty string epsilon, and if a node corresponds to the string sigma, then its left and right children correspond to sigma 0 and sigma 1 respectively. Okay. So just as an example, if let's say n equals 3, what do we have? So we have epsilon at the root, then we have node corresponding to the strings 0 and 1, then we have nodes corresponding to 0 0 0 1, 1 0 1 1, then we have 0 0 0 0 0 1, 0 1 0 0 1 1, 1 0 0 1 0 1, and 1 1 0 1 1 1. So this is my tree T. Now what we will do is that we will define a probability distribution. Okay, so yeah, so we will also define randomly 2 to the power n subtrees of T as follows. Okay. So T1 is just the subtree which consists of only the root node. Okay. And Ti plus 1 I will define as follows. So for a random node sigma at depth less than n in Ti, add the two children sigma 0 and sigma 1 to Ti. Okay. So what you do is essentially that take Ti, take any random node sigma in Ti that is at a height less than n, strictly less than n. Now you just randomly add its two children, and that is my Ti plus 1. Okay. So once again we can look at an example just to familiarize ourselves. So we have this as T0, then in T0 there is only one node, so T1 has to be this tree. Okay, now T2, I randomly pick one of these two, so not just a random node, but for a random leaf node. Okay, so yeah, in a internal node, of course, you cannot add any children. For a random leaf node at depth less than n. Okay, so between these two leaves, I pick any one. So let's say I pick this guy and I add its two children 0, 0, 0, 1. This becomes my T2. Sorry, I start with T1. This is my T2. This becomes T3. Then let's say 0, 1. I pick this one. This is also at less than height 8. So I pick this one. I add 0, 1, 0, 0, 1, 1. This becomes T4. Now I pick this guy. So we have this 0, 1, and I have something over here. Now I add its two children here 1, 0, 1, 1. T5. Now let's say I add children to this guy. So this is 0, 0, 0, 0, 0, 1. This is my T6. And now let's say that T7 is, I mean, you pick any one of these two, that is T7, and the last one will be T8. Okay, so I'll just. So, okay, so this is how I get a sequence of trees T1 up to T to the power 2n. Okay, so now I will use these trees to define distributions over functions. So corresponding to each tree Ti, I will define a distribution. Okay. So now corresponding to each Pi, we define a distribution over functions from 0 1 to the power n to 0 1. Okay. So how do we define the distribution? So let's take a Ti. Okay. So consider some arbitrary Ti. Now for x belonging to 0 1 to the power n, what we will do is we will look at the tree and we will look at so now note that each node x is basically a leaf node in t to the power n. Okay. Now Ti might not have that leaf. Okay. So I will look at the maximum common segment between x and Ti. Okay. So I will look at what is the maximum m, okay, that I can go to, which is common to both Ti and x. Okay. So in other words, let m be the largest integer such that x1 up to xm. So this string is a node in Ti. Okay. So for example, okay, let's take an example here. Suppose my x is, or suppose my Pi is, suppose I equal to 5. Okay, and x is the node, or x is the string 101. Okay. Then what is m? So look at T5. Okay, look at where 101 is. So basically I can, if I actually trace 101, I only go up to depth 2. Okay, so in this case, so then m will be equal to 2 in this case. Right. Now of course the minimum that m can be is 0 and the maximum that m can be is equal to n. Let y be a string chosen randomly from 0 1 to the power k, and now I define the function psi I y of x as follows. So essentially what this function will be is, it will be okay, so I have erased it. So it will be similar to psi y, but after this x. Okay, so whatever is the common part, so that common part, for that common part I will use my tree t, and after that I will basically be composing the function phi. Okay, so essentially this will be phi xn composed with phi xn minus 1 up to phi x m plus 1 of y, and of course I take the first digit of this. So the first bit of this. Okay. So note what we are doing. So till m, okay, so till m basically I have my tree Ti. Okay. After that I am using the function phi to get the value of psi iy. Okay. And of course, so we have to look at one condition. So if what if m is equal to n? So if m is equal to n, then I don't have m plus 1. So we'll define it. So if m equal to n, okay, then just output the first bit of y. Okay, whatever is the first bit, you just output that. So now let's try to understand what these functions are doing. So what happens if I equal to 1? Okay. So that is if my tree is just the empty node or the empty string. So if I is equal to 1, then what is m? M is equal to 0. Exactly. So if I is equal to 1, then m equal to 0. Now what happens if m is equal to 0? What is psi I y of x, or psi 0, psi 1 y of x? I is 1. So it is exactly psi y of x. Okay, because now I am going all the way up from x1. Okay. Okay. The function that we have. On the other hand, if I equal to 2 to the power n, then m will be equal to n, right? And if m is equal to n, then this is essentially choosing a random function. Okay. So if m is equal to n, then what we do is that we just output the first bit. So the function that we are defining, psi 2 raised to the power n of y. So y is a random string. So this is a random function, fine, chosen uniformly. Okay. Now what is our assumption? So our assumption is that by the assumption of our theorem, what we have is that there exists a polytime computable function A such that if I choose f from this distribution, that is I randomly choose it from psi y 2 to the power n. Okay. The probability that it accepts minus if I choose a function from psi 1 y is at least 1 over 2 to the power some kn, okay, 2 to the power minus order n. Now, what does this give us? So, essentially what it is telling us is that, well, if I go from 1 psi 1 up to psi 2 to the power n, if I go through all these distributions, then by the time I go from psi 1 up to psi 2 to the power n, there is an algorithm which is able to distinguish between these two functions. Okay. So, now what does that mean is that there exists some I, okay, there exists some I between this. Okay, let me define a notation before that, it will be easier. So, let Pi be the probability that A of f equal to 1 for f chosen from the distribution psi I of y. Okay. So, what this tells us is that there exists an I such that the difference between Pi plus 1 and Pi is at least 2 to the power minus order n, right. So, I mean, this order only has a difference of 1, I mean additive factor of 1 between the constants that is used here and used here, because there are 2 to the power n many of them. So, what we can say is that, well, if for each one of them it is bounded by less than or equal to 2 to the power kn, then by just summing up this will be bounded by 2 to the power k plus 1n. Now, because this this is bigger than, let's say, some 2 to the power minus kn, this has to be bigger than 2 to the power minus k plus 1 and something like that, some constant that is changing by 1. Okay. So, there exists an I where this is happening. Now, what is Pi plus 1 and what is Pi over here? Okay. So, Pi, note that, is coming from this distribution. So, this distribution is happening with respect to a tree. Okay. So, a tree Ti and a tree Ti plus 1. How does these two trees differ? Okay. So, let us understand the tree. So, suppose this was my tree Ti. Essentially what it means is that there is some node, leaf node sigma over here. This is a leaf node, and in Ti plus 1 what I have is sigma along with its two children, sigma 0, sigma 1, right. This is exactly the difference between these two trees. Okay. So, we now show now we have this as our assumption. Okay. So, from this we got this as the assumption. So, under this assumption we now show how to break the PRG phi. What does it mean to say break the PRG? Essentially what it means is that, so the pseudorandom generator takes a string of length k and produces a string of length 2k. So basically, if I am given a string of length 2k, I have to decide whether it is coming from a truly random distribution or it is coming from this distribution. Okay, that is, given a z belonging to 0 1 to the power 2k, we need to decide if z is of the form, if z is a random string of length 2k, or z is of the form phi 0 y, phi 1 y for a y, a random y of length k. So we have to distinguish between these two choices. Okay. So how do we distinguish? So to distinguish between these two, we will define a function f. Okay. So we define a function as follows. Okay. What we do is, on input x, okay, let tau be the maximal initial segment of x. Okay, so I look at the tree ti, and well, whatever x is going, let tau be the maximal initial segment of x. That is a node in ti. Okay. So look at the part. Okay, so I mean, if I just try to trace x, tau is basically the point till which I am able to stay inside ti. Okay. And let the length of tau be some r. So if tau is not equal, sorry, tau over here, right? Yeah. So if tau is not equal to sigma, that is, well, it went off, it branched off from here, the path leading to sigma at some point, then I will define f of x to be phi xn composed with phi x r plus 1 of y. So just one point over here that I want to emphasize is that the choice of this y actually depends on the node of the tree. Okay, so when we are saying that I choose a y randomly, it is for a node. Okay, so once I have a node of a tree, it is with respect to that node over there. Okay, okay. So fx is defined in this way, and if yeah, so again, so once again, it's the first digit of this. So the first bit of this string, and if tau equal to sigma, okay, so basically let's say that it went to this node and then it went ahead, then what we do is that fx is equal to first bit of phi xn composed with phi x r plus 2. So basically I go one more level down over here, and now I take the left half of z if x r plus 1 is equal to 0, and it is equal to the first bit of phi xn phi x r plus 2 right half of z if x r plus 1 is 1. Okay. So basically the other case, if r plus 1 is 1, then I take the right half, and if r plus 1 is 0, I take the left half of z. Okay. So now let's try to analyze, and this is the definition of my function f. So now how is this function able to distinguish between the two? So now note the following. So if z is of the form phi 0 y phi 1 y, right? Then what is f? So there are two things for f, if tau is not equal to sigma and tau equal to sigma. So look at the first part. If tau not equal to sigma, then f is basically the same as what was the notation? So psi I of y, or psi r of y in this case. No, sorry, psi I of y. Right. So it is basically the same as that. And if tau equal to sigma, okay, what is the left half of z in this case? So the left half of z depends on this bit, so x r plus 1. What is the left half of z if xr plus 1 is 0, it is basically this. And if the next bit, if xr plus 1 is 1, it is basically this. Okay. So if z is this, then f is essentially drawn from the distribution psi I of y. Okay. So that is f of x is equal to the first bit of phi xn up to phi r plus 1 of y over here. Okay. Now, if z is, let's say, a random string in 0 1 to the power 2k, okay, in this case note that this does not have any significance, right? Because well, y is a random string and this part actually does not depend on z at all. But the part that is dependent on z is the second part, that is when tau equal to sigma. And here, because z is a random string, both the left and the right part are essentially just a random string, right? So therefore, this is basically going up to tau r plus 2. Okay, so if you the tree got erased over there, but essentially this is corresponding to the tree ti plus 1, the distribution that we got from ti plus 1. Okay, so therefore, if z is a random string over here, then f is drawn from the distribution psi I plus 1 y. Okay. And well, this distribution corresponds to the tree ti, and this corresponds to the tree ti plus 1. So therefore, what we have, so our assumption is that we can actually, there is an algorithm which is able to distinguish between these two distributions. Okay, so therefore we can distinguish between the two choices for z with probability at least 2 to the power minus order n by a polytime algorithm. Okay, so therefore it means that h phi is at most 2 to the power order n, right? So this is polynomial time, and this is just 1 over m, which is 2 to the power order n. Okay, so this completes the proof of this. So essentially the idea is, I mean, the intuition here is that we are assuming that we can break a pseudo-random function generator. There is an algorithm which is able to distinguish between two functions, one a truly random function, another drawn from a specific distribution. And then using that, we are able to show that if we start off with a PRG, we can able to distinguish between a string that the PRG generates versus a string that is truly random. Okay. So yeah, so this completes the proof and also the last topic of this course. Any questions? It's not a natural proof, because if that was a natural proof, yeah, it wouldn't have implied anything, but no, that's not a natural proof. Okay, so just to give a quick recap of whatever we have seen in this course. So we started off with this lower bounds on circuit size. So essentially we saw Shannon's lower bound, that is there are a large number of circuits which have circuit size at least 2 to the power n by n. Then we saw Shannon-Riordan's theorem, which gives a similar type of lower bound, but a little stronger lower bound for formula size. Okay. Then we saw that well, if we look at formulas over the De Morgan basis, then by Kravchenko we get even better lower bound. We saw Necheporak's theorem, which essentially showed that we can actually give a lower bound for a formula in terms of its sub-formula or sub-function. If I take a function, I can give a lower bound for this function in terms of the sub-function. Then we saw Subotovskaya's theorem. So Subotovskaya's theorem, once again, it gave a connection between, so suppose if I have a function and I look at a random restriction of this function, so what is the or what is the connection between a depth lower bound for the original function versus the depth lower bound for this restricted function? So that connection was given by Subotovskaya's theorem. Then what else? Then we moved on to some constructions, some upper bound result. We saw that what did we do next? We can give a monotone, a polynomial sized monotone circuit family for majority. Okay, essentially Valiant's construction. And then we moved on to various arithmetic operations. We saw that if you look at addition, we can start by very simple construction of getting a order n depth circuit, which can be improved to order log n depth circuit with n square size, and that can even be improved further to the most optimal case, that is log n depth and linear size. Okay. Then we saw for division, we saw that we can get division in NC1 due to this famous result by Beam, Cook and Hoover. What else? So after that, yeah, so after that we move to lower bounds once again, and we saw the monotone lower bound for clique due to Rasborov. Okay, so if you look at the clique function, and suppose since clique is a monotone function, if you look at a monotone circuit for clique, what can we say about its size? Okay, and then we argued that, well, the size, the monotone, I mean, if you have a monotone circuit for clique, then it would require size that is exponential. Okay. Then we saw Rasborov-Smolensky's result for lower bounds on mod k function. Okay, so for any mod k, if you want to have ACC0 Q circuit, okay, where Q is some other prime and K is, let's say, some prime, then it requires not just super polynomial, but in fact exponential size. That is one way of showing that parity is not in AC0. And then we saw Hastad's result, which is another way of showing parity is not in AC0 by using the switching lemma. So Rasborough-Smolensky was based on this polynomial approximation of AC0 circuits, or polynomial approximation of gates essentially, which led to approximation of the circuit. And after that we moved to branching programs and saw that well, NC1 can be actually characterized as in terms of branching programs as well, more specifically branching programs of width 5 and polynomial size. And if we come down to width 3, then that corresponds to a very specific family of circuits, namely this what was it, mod 3 composed with mod 2 circuits. Okay, just depth 2 circuits that have a mod 3 gate at the top, followed by mod 2 and then inputs below it. We also saw connection between communication complexity of a function and the circuit size of that function. So what does it mean to say that, I mean, how can I get a lower bound for a function if I know its communication complexity and vice versa. And finally, we saw that well, these various lower bound techniques for proving lower bounds for circuits essentially do not suffice if we want to separate NP from P/poly, okay, which is kind of the holy grail of circuit complexity, to show that if I take an NP complete problem, I cannot do it, I cannot compute it using poly-size circuit. So all these various results kind of led researchers to believe that probably we can separate NP from P/poly, if not NP from P. But this natural proof barrier due to Rasborough and Rudic kind of showed that any natural proof will most likely not work. Okay. So that is a very brief overview of what we have done. That can definitely work, yeah, those methods can work. But the point was that at that point in that 1980s, early 90s, all the circuit lower bounds that were there were actually exploiting this natural proof. Okay, so essentially it showed that if you take a function, you take a hard function, then that function satisfies a certain property, but any function that is computable by that class does not satisfy that property. Therefore, that function is not in that class. That was essentially the idea of showing lower bound. But now if that property is a natural property, then we showed that most probably that will not work for NP versus P/poly. And all those properties indeed were natural properties. That is what has been shown. So we did not get into that part, but that was shown in the paper by Rasborough and Rudic as well. I mean, in none of the non-trivial classes. Well, you can argue it is not in AC0. Parity is not in AC0, but nothing non-trivial. Not even in ACC0. You can't even say that if you take a function from NP, it cannot be solved by a bounded depth circuit which has arbitrary mod gates. NC1 also nothing is known, because ACC0 is contained in NC1. Any mod can be simulated by log depth. So nothing is known with respect to NC1 as well. Okay. Okay. So we'll stop here.